All right, settle down, settle down. Hey guys, thank you for joining us. We're right on the money, 12:59. Let's get started, okay? We're probably gonna do a roll call in the middle of it. So 2 mini lectures today, you know that, right? I don't see a whole lot of coffee. I see a power gate. Oh, that's good, right? Gatorade, what they call it? Sorry, lost my touch. 10 years now since I play sport. Anyway, so now, good things. We are going to get some calculation done today. Hooray, right? Just me? Sure, of course. But not a whole lot. Okay, so it won't be too hard for you. We're gonna have a 45 minutes lecture. We're gonna take a water break for 5 minutes. I don't know if the water fountain working or not. So maybe water means that of water. You get a drift. And then we're gonna resume and start second lecture and continue on around like 2:30-ish. So we'll be done, okay? Maybe 2:35 latest. Not too bad, right? Not too bad. Now, I know some of you might have an appointment from 1 to 3 for the shot. Take it, okay? Take it. You won't die, all right? Oh, it's on recording. Okay, fine. That's what I feel like the vaccination, okay? You won't have a problem with it, okay? So if you haven't taken the shot, please, I encourage you to take the shot, okay? Vaccination. All right, that's about that. So what we learned from last time? Sounds good. So 1.2 what? That plus what? There you go, you got it. Okay, so what else we learned? The lecture before that. Concrete is good for what? Compression, right? Steel is good for what? Tension. You gotta have two parts work for you together, right? So that's what we have learned, isn't it? Okay, so code. You have known that you should get ACI 19, ACI 31819, right? How many of you still haven't got it? Okay, 1, 2, okay. Need it before spring break for sure, right? Exam is gonna happen. You'll be unlucky if you don't have the code at the time. Online, heard that? You got to get a code, okay? All right, so that's about it, ACI 31819. Okay, now what we also learned from, shoot, this is not open yet, sorry. What we learned from the concrete properties last time, 1 second, okay, this thing is warming up, is that concrete have paste and aggregates. Paste and aggregates. We know also that we're using what kind of test method to get compressive strength out of it? What do we use? Hydraulic, sure. But what kind of test samples? Cylinder, right? So 2-cylinder size, which are the 2-cylinder size we used? 6x12, right? And 4x8. Okay, so that's what we get. And sorry, it's just thing is, don't like this stuff. Okay, so there we go. That's what we learned, okay? And now we also said something about the modulus of elasticity, right? Modulus of elasticity. So I need to share screen apparently so we can get it recorded. So let me do that as well, okay? So for that, there we go. We have a nice nonlinear curve, right? In terms of stress and strain. The definition of stress pound per square inch, and definition of strain is elongation over original length. So what is a unit for strain? No unit, right? So 1 is the unit. Okay, so now if that's the case, and the modulus of the elasticity or Young's modulus for concrete is defined as the slope of this linear curve that is equal to stress divided strain. Given that the unit for stress is PSI, what is your unit for the modulus of elasticity? PSI. All right, so good. That's what we learned. Okay. All right, so next stuff, right? So we now know we have to test the concrete cylinders. And there are standards, right? 25 pence per layer, 3 layers for 6x12. Similar things go to 4x8. Might be a little bit different, but that's all we know to prepare cylinders, right? And we prepare cylinders according to ASTM standards, C31, C39. Okay. If you have doubts and worries, go to that and find out the details. Okay. Now, next step, compressive strength of concrete. We call the peak stress of the stress strain curve F prime C to be the compressive strength of the concrete. And everything, when I say everything, that means modular elasticity, the tensile strength is related or are related to this F prime C. So all we need to do is to get F prime C and estimate the other properties for concrete. Okay, all right. You need to know this. As concrete strength goes up, the stress-strain relationship of the concrete goes this way. What do I mean by this way? You see this curve was originally flat, now become a little bit sharp, meaning the strength increases, but the failure strain or ductility reduces. Okay, now nature of law of nature for materials, right? Any material that is high strength, usually brittle, okay? Any material that is low strength, usually tough, ductile. Give me some example. Concrete being high strength, brittle, what the other component? What's the other material that is low strength, okay, not steel, low strength, but ductile? Rubber, right? Tires, your cars, right? That's the example. So similarly for concrete, the higher strength you go, the more brittle it is. So what does it mean, or what does it imply in terms of design? If I have high strength concrete and compared to a low strength concrete, what do I need to do to ensure it is safe? Increase ductility. What should I do? Add steel reinforcement. Got it? So for UHTC, what is UHTC? Ultimate high strength concrete, right? You've seen that a lot for a lot of building structures and bridges out there. Why do we use UHTC anyway? Why do we need high strength of concrete anyway? Is to what? Reduce the section size so we can build slender structures. But the sacrifice is what? We need to add a lot steel. We need a lot of steel. Okay, so that's the original concept coming from this curve. All right, so that is that. And now we have a lot of delicate parts of this thing, right? You need to get the initial tangent modulus and B and A, all that crazy stuff. I will talk about it in terms of writing right after the slide. So this for now, just for you as a sightseeing purpose. Okay, one thing you take away right now is EC here in terms of modulus of elasticity or Young's modulus, right? Young's is a guy who discovered this thing, right? Way ahead of Hooke, right? That is EC equal to 57,000 square root of F prime C. Square root F prime C. So now F prime C is in terms of PSI. So what is square root of F prime C is? What is the unit of square root of prime C? What is unit of that? Square root of PSI, isn't it? Wrong. In this case, this is empirical equation, okay? Note that this is empirical equation. So there is no square root of PSI, okay? You just take the number in terms of PSI, but leave the unit there. So modulus elasticity share the same unit as F prime C. Remember that, okay? Now, let me ask a question. I am on site. My guy told me the concrete is 4 KSI, okay? And what is my Young's modulus? What is my modulus elasticity? Don't stare at me. Do you want me to do Siri or pull out your calculator? Let's punch the numbers, right? Pull out your calculators, do it, right? 57,000, right? And my concrete is F prime C, curbside concrete, pick up from Rolla Ready Mix, 4 KSI. What do I have for EC? Come on, you have the equation. 57,000 square root F prime C. What do you have? I'm considering giving bonus who the first one shouted out the correct answer. Say it again. Oh, that's a nice number. What else? I'm not saying that's wrong, okay? I'm just saying that's a nice number. You got different? PSI, right? Okay, that is correct number. But do I get something different? I wonder, do I get something different? Let me ask you this way. When you pull out the equation, how many of you plug in F prime C equal to 4 in the equation? Don't tell me. You know who you are, right? Don't use KSI, okay? Let me repeat. Under the square root sign, it's always 4,000. It's always 4,000. That's where you get 33 million. That is the correct number, okay? Understand, okay? You may laugh now. I have 30 students out of 70 students. First exam made the same mistake like this, okay? And I said it twice in my lectures, okay? So gotta remember that, okay? So that's all you need to know for concrete properties. All right, tensile strength of concrete. Here for this slide, all you need to know is about 8 to 15% of compressive strength. Let's take the average, 10%, right? 10%. So if I have a 5,000 PSI concrete compressive strength, that is, what is the tensile strength of it? 10%, what is it? 500 PSI. Is that right? 500 PSI. Okay, remember that. All right, so that is for that slide. Simple, right? So how do we test it? How do we get that number? We use this so-called 3-point bend. So make a concrete prism, right? Like a beam, and we bend it in the middle. Okay. The stress generated from this fixture is FR equal to 6N over BH squared. What does N mean? You've seen this from mechanics materials. What does N mean? What is N? Moment, bending moment, right? Now in this picture, if I have a simply supported beam, let's assume the span length is L. All right, it's not there, but let's assume it's L. And I have a force equal to P. What is M? Give you a hint. PL over 4, right? Why there's a 4 there? Because the M equal to the reaction force on each side multiplied by the lever arm is the distance between the center point load to the reaction, that is half L, right? So half P multiply half L, you got PL over 4, and that is the maximum moment in the middle. Okay, so 6M over BH squared, and you get the tensile strength of the concrete. Let me ask you this again. The crack will start from the top or the crack will start from the bottom? Bottom. Why is that? Because that's where the tensile stress tension is at. Great, okay, that's it. So there are other ways. We also do 4-point load instead of 3-point load. And why we're doing 4-point load? Well, because the moment is different, right? So for the 3-point load, what is the moment diagram look like in your heart, in your head, maybe? What does the moment diagram look like for a 3-point load? Hint, triangle or rectangle? Triangle, right? So that means I only have one spot that has a maximum moment, which is the middle of the beam. Is that right? Okay. For 4-point load, you will have a so-called constant moment zone. That means in the middle section, there's the entire zone has the same moment, right? Has the same moment. So answer me this. You do a test, right? One with 3-point load, one with 4-point load. Which one you have a lower number? Which test will give you a lower number? Let me ask you again, and gentlemen, that is not on your phone. You have a 3-point load and you have a 4-point load, okay? And you do 2 tests, same beam, identical, okay? Now, which number is lower, from the 4-point test or a 3-point load test? Why? Because there's a higher moment in the middle. Let's assume it's the same moment. That's a good answer. So my fault. Let's assume same moment though. It's more concentrated. So one part has to experience. Let me transform to something you probably know. Do you guys play Powerball? Lottery? No? Just me? Oh my God, you guys are rich. I go to the gas station, right? I buy myself a ticket, right? If I buy 1 ticket versus I buy 100 tickets, which way I have a higher chance of winning it? 100 tickets, right? Now try to use the same logic here. If I do 4-point load, I have an entire area have the maximum moment here, right? I have 3-point bend, right? I have only one maximum moment in the middle, right? So which one has a higher chance of filling it? 4-point, right? So which one has a lower number? 4-point, right? It's a number game, right? Probability, right? You know this, you can play in the Wall Street as well, right? Might as well Las Vegas, right? Go, baby. Not too hard, right? Okay. So that is difference, okay? So that's why we usually go with 4-point load to get a safer number, okay? Now, what is the reason we don't go with 4-point load? Because it's harder, right? It needs more setup. It's not quick. So most of the time, we still stick with 3-point load because it's simpler. You just need one wood sham, all right? Oh, lazy me, right? Just want to do one sham, but that's what it is, okay? All right, so you got it. Now, the other test for tensile test, this is also for tensile set test. We call it split cylinder test. We do a 6x12, shovel it under the MTS machine, have a sham running through right on top of it, and apply pressure in the middle of it and split it open, just like you split watermelon, right? Just like you split watermelon. Have you played karate before? No? Yeah, a little bit think about how watermelon split, right? That's what you do, right? You go, ah, and then split, right? Same thing. So what we learned, compression converted into tension in the middle section here, okay? Now, quick question. You also have the 3-point bend, 4-point bend. You have a split cylinder. Which one out of the 3 give you the lowest number? It all depends on stress distribution, isn't it? It all depends on the stress distribution. So for split cylinder, you have a tensile zone, but you also have some compressive zone on the top, right? So the chance of failure is actually a little bit higher for the split cylinder. So split cylinder will give you a lower stress, Okay, so that's what we learned, okay? Now compare to the 3 tests before we go on, compare to the 3 tests, I want you to write some number down. For the beam, okay, the obtained tensile strength from the beam usually is called modulus of rupture. It's not on the slide. You have to understand my accent English, but it is called modulus of rupture, MOR, okay? Write it down, modulus of rupture, okay? And that number is represented by a symbol F with a subscript R, and undercase R, okay? Now a big R. And that equal to 7.5 square root of F prime C. Here, F prime C take as PSI, okay? PSI. So that is from the beam bending experiment. For 4.3 point, that's the estimation. For split cylinder, usually it is 6.4 square root of F prime C, okay? Estimated, okay? Empirical estimation, 6.4 square root F prime C. So you see that which number is lower for same concrete strength? Split cylinder. So remember that, okay? Remember that. I will ask you that in the exam, okay? But we usually don't use the split cylinder test results as for design. We use the 7.5 square root F prime C for design purpose, okay? And that 7.5 square root F prime C usually equal to a 10% of concrete compressive strength, okay? If you don't believe me, let's do a quick calculation, right? Take out your calculators, right? Plug in this, right? 7.5 square root of 5,000 PSI, what do you get? 7.5 square root of 5,000 PSI, what do you get? 530, right? What is 10% of 5,000? 500, right? That's close, right? That is close. So that's where we use, okay? Not hard, isn't it? Class is simple. Remember these key numbers, okay? So that's what we learned about the concrete, okay? 6.4, don't worry about 8.3, use that 7.5 underneath, okay? Now, this 8.3, just forget about it, right? For now. And 6.4 is for split cylinder, right? You call it, you see that FCT, split cylinder, okay? Now FR, modulus of rupture, is 7.5 lambda square root of prime C. What is lambda? Lambda is a special factor. For normal weight concrete, it is 1.0. For lightweight concrete, it is 0.75. Now, why for lightweight concrete, you have a lower lambda value? Why is that? Because what is in the lightweight concrete? What does make it light? Here, that's right. So what's the main difference in terms of composition of the lightweight concrete and normal weight concrete? Now the cement is the same. We're not going to get anything different from cement. We bought it from Lowe's and from Home Depot, I don't know, right? Mix them, right? The water, same water, right? Maybe it's the hard water, soft water, but it doesn't hurt, right? The only thing difference between the normal weight and lightweight is what? Aggregates. So for the lightweight aggregates, what? It's porous aggregates, right? Empty aggregates, shell aggregates, things you dig out from ocean, things you dig out from the rivers, right? River sand, light, porous, weak, right? So that's why you have a 0.75 reduction factor to consider for the tensile strength of it, okay? So that means if I have the same strength for normal weight concrete, same strength, I'm talking about compressive strength for lightweight concrete, which one have a lower tensile strength? Which one have a lower tensile strength? Lightweight, right? So for lightweight concrete, do I need to add what? More steel. I need to add more steel for lightweight concrete, okay? Common sense, all right? So you want to become an expert, or at least pretend to be an expert on the job field, right? Somebody asks you, Bob, we have some crappy concrete. What do I do? Add more steel in it. There you go, okay? All right, so that's the idea. And then quickly, I want to get through this stuff. So concrete will change its volume. Concrete will change its volume. It will shrink, okay? It will creep and it will expand under temperature, okay? What is the shrinkage? What causes it to shrink? Well, I don't know, Bob. It naturally like to shrink, right? So what components has to be taken off to make it to reduce its volume? What's in it? Water, right? Water is the only thing that evaporates and will shrink the concrete, okay? What kind of problem you anticipate if shrinkage happens? Cracking. Why is that? Because when you reduce your volume, but your boundary is still fixing it, you are generating what? Tensile strength inside your concrete, so you crack. Okay, so that's called autogeneous cracking. Autogeneous cracking. Okay, all right. So creep. What does creep mean? Creep means if my wife is cooking, I don't want her to know because I don't want to do extra work. I follow her from kitchen to wherever she's going, and she just didn't realize that means you're creepy, Bob. But that's not the same creep we're talking about here. Creep, by definition, is a permanent deformation caused by permanent load. That means if I become a Shaolin monk, apply my palm on my table, right? The Bai Mei palm. Watch Kill Bill. Not much. Oh boy, you guys lost out. Anyway, so I apply 100 pounds of force, right? Apply on it for a second, nothing will happen. I sit on it for 100 years, right? Oh, I'd be a bones then, right? But 100 years of load, you will see a palm shape, right, in the table. That means creep. That means creep. Okay, it's not much of load, it's permanent. Okay, forever. Okay, so that is same as footing foundation settlement. Have you seen crack on your footings of house? At your house, right? Some cracks there. Settlement. What is settlement? The earth underneath it creeped. Okay, and that creep mechanism is different from our concrete creep mechanism. That creep mechanism comes from water from the soil, but our creep mechanism for concrete is slightly different. So let's talk about the creep a little more. Okay. Now there are several stages of the creep. As I apply load, there's an immediate strain deformation happening in the concrete, right? You see a spike. And as I keep applying the load, you see a little bit more increase of a strain going up to a peak. Then once I remove the load, there's so-called elastic recovery, meaning some part of the strain recovers, going back, okay? But afterwards, keep creeping, and whatever left is called a permanent deformation. And this part is the creep of the concrete, okay? Now, what does it mean? It means that you guys taking the survey class, right? You take out equipment from somewhere down in the hall in the BCH, right? Next time when you take out equipment, look up, there's a giant crack there, right? And that is caused by the creep, okay? And don't tell the professor I said that, okay? It's supposed to be a secret. All right, so that's about concrete you need to know for design purpose, okay? All right, a lot of visual, a lot of quick ideas. And you need to remember all this for your exam, but I don't have to read it. I think you can comprehend and remember this, okay? Now, critical things, steel. For reinforcing steel, how many of you guys have worked with reinforcement before? One guy, two guys, okay. How many guys actually bend the stirrups yourself? Bend the stirrups, no? Am I the only guy here bend southern stirrups? All right, so I am the only guy. Okay, great. So you've seen the reinforcement, right? Is it smooth? Is it smooth shining like a mirror? No, right? It is usually what? Deformed, ripped, right? What is that ripping for? Surface area for what? For friction, right? For a better bonding with the concrete. Interaction, friction, adhesion, right? With the concrete. So every reinforcement you see out there, right? Unless it's a wire mesh, it is deformed. It is deformed, okay? Hence, we call it rebar. We call it rebar. Okay, that's the concept of it. Okay, so normal reinforcement we call it deformed bar or rebar. We have welded wire reinforcement usually for thin slab on walls. We have pre-stressing steel. Okay, now we talk about pre-stressed steel in the pre-stressing concrete class, but this is for rebar. There are ASTM standard 615, 706. All these are the properties in 996. Just need to read them. And now here's the critical part. You will see this symbols on the rebar. H representing the mill that is being produced. 11 means it's bar size, and S means it's type of steel, okay? Usually are hot rolled, okay? We don't have cold form steel for rebar, okay? Why is that? We have cold form structures, right? You will be taking lessons from cold form structure later in your life, okay? And hopefully Dr. Labou teaching, I don't know whether he's still teaching that or not, but what is different between cold drawn or cold form steel and hot rolled steel? Temperature, sure, but in terms of mechanical properties, what are the differences? Ductility, and well, that's right. What else? So have you taken the materials lab before, testing the steel, tested steel before? No? Okay, so next time we do that, right? You put a hot rolled steel and you put a cold form steel, right? One behave like a nice smooth line, okay? There means no yielding point. no yielding point. That is cold form. That is cold form. Hot steel has a yielding point. Okay, hot rolled steel has a yielding point, and this is the yielding point I'm talking about. Okay, why is that? Because hot rolled steel goes through a rapid annealing process. What is annealing process? You bring up the very high temperature and quickly cool it down. How many guys into the night forging TV shows on Netflix, forging in the fire, something like that, right? There's always a critical step that what is anneal your knife, right? Quench it, right? What is quenching? You bring in a very high temperature, you quickly lower the temperature down where the grain in the steel crystallize, right? Become finer, so become stronger, right? So then you have the sharp point, it's called yielding point. Okay, so when you test a hot rolled steel, you have this nice linear response till you reach a certain limit and goes back and goes up again. And this portion up again is called hardening portion. Hardening portion. What does hardening mean? Means that I keep increasing my strain at the same time my strength increases. Okay, then goes over the peak. As I keep increasing the strain, my strength reduces or decreases, right? And that is called softening behavior. Okay, so yielding, quick plateau, hardening, softening. Okay, then what happens? Fractured into cone-shaped fractured. Okay, so that is the curve, but that is too complicated for our design purpose. Imagine you have to do computer machine learning to get this curve in your design code. That's going to be a nightmare, right? So what we do is simplify it. So this dashed line representing the ideal stress-strain relationship for the steel. So what is the feature of this dashed line? Looks like very simple pieces, right? Two segments to be precise, a linear ramping up stage and then a horizontal plastic stage. So we also call this one in Latin elastoplastic. Elastoplastic, meaning first part elastic, then plastic. Okay, plastic. Now again, what does plastic mean? What does plastic mean? I don't know, Bob. Plastics, you know, everything's rubber, right? Everything's plastic. No, that's not the same word. Plastic means like Play-Doh. When you apply stress to it, right? It does not increase the strength, right? No resistance, which means the strength or the stress in the steel after hitting the yield strain will stay constant, That means if I tell you the yield strength for my steel is say 60 KSI, meaning that steel will never exceed 60 KSI. Okay, meaning you're done. You only get 60 KSI as much out of it from your steel. That's it, no more than that. Okay, so for us, two parameters important here, actually three parameters. One is called Young's modulus of steel ES, and the other is the strain of steel epsilon S, and the other is FS, the stress of steel, and you need to know that it has a yield strength of FY. Okay, FY. Okay. If this is too much, don't worry. I'll write them down, explain to you in detail, okay? But right now, just want to fly by, you see the concept, get this outline in your head, okay? All right, so that is the stress steel curve. Now, great. You heard them on the job site. Whoa, Joe, what steel are you using? 40? What steel are you using? 60? So they shout out 40, 60. What does it mean? It's grade, right? Grade 40, grade 60. So what does 40 mean? 40 means 40 KSI for the yield strength FY. Okay, 60 means 60 KSI for the yield strength FY. Okay, why that is so important? Because you need that for your design. You need that number for your design. Okay, now the structure steel you see in the lab or you see for the buildings usually are 50. Okay, for stirrups, for shear, usually are 40. For main reinforcement of rebars in the bridges and everything, usually 60. Okay, for World Trade Centers, high-rise buildings, usually go with 75. Okay, you want to sound like a pro, you need to know these numbers. Okay, all right, so that's it for these numbers. All right, so that is how much we need to know about steel. Is it last slide? Okay, yeah, almost last slide. One more thing. Bar size. So in United States, we go by English unit, right? So we go with bar size, these numbers, number 3, number 4, 5, 6, 7, 8, all the way to 18, okay? And the area, which is the cross-section area of the bar, right, is provided here as well. And you need a way to consider for transportation. You also have a diameter of the bars. So let's see, there's a secret hidden here, okay? For number 3 bars, my diameter is 0.375. inch. So roughly it's 3/8. 3 divided by 8, isn't it? Okay. All right, let's keep going. Number 4, I have 0.5 inch. That is what? 4/8. 4 divided by 8, isn't it? So number 5 is what? 0.65. That is what? 5/8. 5/8. Right? So what is number 9? Sorry, what is number 8? What is it? 8/8. So that is what? 1 inch. So you got it, right? Every size increment representing 1/8 of an inch. Okay, so our bars go by 1/8 of an inch. Okay, 1/8 of an inch. All right, so if I throw a number out, number 7 bar, what is the diameter of the bar? 7/8. That's it. Remember this? Okay, so you don't need to go by any manual, any book. You go out on the field, you're like a pro, right? For bar number 8 or 1 inch. Okay, all right. So another secret. This 1 inch is in terms of diameter. Okay, can I use that to calculate the bar area, which is what? Pi d squared over 4. Can I do that? Well, let's see, right? Pi d squared over 4 for number 8, that should be pi multiplied by 1 inch squared divided by 4. That roughly equal to 3/4, right? 0.75, right? Is that the area I'm getting for number 8? What do I have for number 8? 0.79, isn't it? A little bit higher. So why it is not the calculation I just said? Why has to be this number? What did I forget? The surface, the texture. The texture is what? The rib, the deformed bar, right? So you go back to see the slide, right? Immediately you thought about this slide. You see, it's not perfectly round. It's not perfectly round, okay? These 1 inch diameter is so-called nominal diameter. They're not precise. You have to consider the deformations, the rib, right? So when you calculate the area of a bars, unfortunately, you cannot go from bar diameter to area. You have to remember these areas, okay? You say, Bob, that's a lot of memory. I don't do that. You know, my computer does, that's not me. I cannot do that. That's fine. So there are critical numbers you need to remember. Number 3, mark them down, is number 11. Sorry, 0.11 inch squared, okay? Number 3, 0.11 inch squared. You will use this again, especially in chapter shear part, chapter 6 or 7 shear part, okay? Number 3, 0.11 inches. Number 4, 0.2 inch squared, okay? Then number 6, 0.44 inch squared. Number 8, 0.79 inch squared. And my personal favorite, number 9, 1 inch squared. Do you get it? Why is my personal favorite? When I give you the exam, I need to put a bar there, right? I'm lazy. I don't want to do fractions. You know, imagine that, right? Bob doesn't want to do fractions. Sure, I don't want to do fractions. So I say for number 9 bars, So how much total steel I have in terms of area in the cross section? For number 9 bar, that is what? 4 inch squared, right? So that's why it's my personal favorite. It will become your personal favorite as well because you do exams, right? You do exam. Remember that, okay? Remember that in case you forgot, okay? All right, so that's about it. Okay, now we fly by the concrete property and steel properties in the Jiffy. Very happy, right? Should we go home now? Should we go home now? Yeah, sure, right? Why not? No, I'm sorry, right? Hell starts now, okay? Let's get into the mathematical sides of it, which is my true favorite, okay? All right, so let's start, take a look at the equations and all the beautiful things that we will have, okay? So first of all, don't save it. Let me share my screen. Okay. All right. And can be a little bit time consuming since I'm playing 3 technology at the same time for 30 years old me, Bob. This is really hard. So forgive me, have a little patience. Okay. Trying to make it large, you see. But if it's too small, just shout at it, make it bigger, and I will do that for you, okay? So open up this slide here. Okay, like I said, hell starts from now. All right, so lecture 1, basic properties for design, okay? Please pull out your notepads, iPads, what Surface Pro, whatever you have it, right? Let's start it, okay? Basic property for design. Okay, all right. So we talk about concrete properties, right? So let's say compressive strength of concrete, okay? We have talked about it. And that's a lot of information, right? So you will need to know these following for the exam, okay? So first thing, F prime C is the compressive strength of the concrete, but that is a 28-day strength using this fellow here, cylinder compressive test, okay? The term is uniaxial compressive test. Okay, uniaxial compressive test. Okay, that's one. Second, now before I continue, why 28 days? Why 28 days? So for concrete, there are 3 days. Why 3 days? Our fellow SCI expert, why 3 days?
Sometimes the contractor wants to know what the concrete strength is that day, so they can either drive over it or hurt around it.
Yes, so shoring structures, meaning they want to see if that can hold load, right? So early strength, 3 days, 7 days, usually for construction, but those don't matter. Those don't matter, right? At the end of the day, when they check or inspect the structures, you have to use the 28 days because that time concrete should be hardened. If you cannot hit 28-day strength, you're in trouble. You're in trouble, okay? So when somebody asks you, what is F prime C? You tell them it's compressive strength at 28 days. 28 days. So quick question here. If the strength does not hit 28 days, what you do? You wait till 56 days. You wait till 98 days. And then there are no more cylinders. Then you're really in trouble. So we go to law, go to court, go to lawsuits, and see if we have to demolish the whole thing and build it again. And this does happen. Does happen. Unfortunately, it does happen. Okay, not the entire building, but partial of it. Okay, all right. So that's about it for this one. Okay, and why am I still doing this? Hold on. Yeah, okay. Let me resume on online because the student not seeing. Okay, good. So that is for the compressive strength. Now, and let me just add this one, compressive tensile. Okay, sorry about that, tensile or compressive. Okay, another thing, FR, we call it modulus of rupture, right? Modulus of rupture. Okay, and that is FR using the beam 6M BH squared in your head. It should be a small, tiny beam here. And you can draw that on your crib sheet, supported at 2 ends, have a force there. And the length of that is half L. So M equal to PL over 4, okay? And then B is the width of the section. H is the height of the section, okay? Should not make mistakes. That's how you calculate the strength from the test. Now, the third thing, FCR or FCT roughly equal to 6.4 square root F prime C, smaller than FR equal to a 7.5 square root F prime C. And knowing that F prime C is in terms of PSI, okay? In terms of PSI, no KSI here, okay? So you see, that's all you need to know for exam, okay? For exam, okay? For concrete properties. Now steel, okay? For steel. All right, so we just shown you. In terms of steel, we call it stress in the steel Fs, okay? And the strain in the steel epsilon S. And if I want to draw a curve, it goes like this, linear line, elastoplastic, the horizontal flatten out, okay? And now this value here, we call it Fy. Fy, Y representing yield, okay? So-called yield strength. And this slope here is called modulus of elasticity for steel. And ladies and gentlemen, this number here, you will need to remember that is 29,000 KSI, okay? 29,000 KSI. What is modulus of elasticity for steel? 29,000 KSI. What is the modulus of elasticity for steel? 29,000 KSI. What is the modulus elasticity for steel? 29,000, great. Why you need to remember this? Because in exam, I will not be giving you that. Okay, I will not give you that. You need to remember this. You may, why, Bob? Why make my life harder? It's not me, okay? It's the society, blame them, right? Because on job site, nobody will give you a book, okay? Nobody will give you a book, all right? These numbers need to remember, okay? All right, so that is 29,000 KSI, great, okay. We need to know Fy is so-called yield strength. So-called yield strength, All right. And we also need to know that depends on the grid. If it's grade 60, Fy equal to 60 KSI. If it's a grade 40, what is Fy, folks? Come on, 40 KSI. Again, I will not tell you in exam what is the yield strength for the steel. I simply will say grade 40, grade 60, and go figure. Okay, remember that. All right, so last thing, bar size. Okay, for a number 5 bar, what is the size of the bar, folks? 5/8, right? So go by 1/8 of an inch per increment. Okay, need to know that. Okay, all right. And my favorite, personal favorite, number 9-inch. That is 1 inch of bar diameter. What is the cross-sectional area of a number 9 bar? Did I make a mistake here? You bet. Is that 1.2? Yeah, that is the diameter of number 9 bar, right? Because that is 9/8. And area is 1 inch squared. I made a mistake just now, and trust me, likely you'll make the same mistake, okay? Number 9 bar, the diameter is this, and this is the cross-sectional area, okay? Don't get confused. All right, okay, so number 8 bar, what is the diameter for number 8 bar? 1 inch, okay? You guys can get confused. All right, so let me rewrite this, okay? Should be 9/8 in terms of diameter, okay? Okay, for number 9. For number 8, it's gotta be 1 inch in diameter. And for cross-section area, what is cross-sectional area for number 8 bar? 0. If you remember that number, 7, 9. You have to remember these, okay? Number 8, number 9, okay? Well, we're at it. Number 4, what is the diameter of number 4? 1/2 inch, right? Or 4/8. What is the area for number 4? 0.2 inch squared. Now, number 3, for the diameter of number 3, 3/8, right? So 0.375 inch. Area 0.11 inch squared. Remember this, okay? It's okay, you want to put on a creep sheet, but you need to remember this to be fast in exam. We have very long exam usually, so fast is the key, okay? Speed is the key. All right, clear. Okay, so not so much, not so bad, isn't it? All right, so before we move on, we talked about live load and dead load. You will have homework today, okay? So let me give you some quick example to help you, all right? Say I have a beam like this. All right, and let's make some examples, put the number in here. So the beam has a span length 20 feet. So happen that I have a dead load, a PD here, equal to 8 kips. And that is right in the middle of the beam. And I have a live load here. Let me use a different color, PL, on top of the PD. And that PL is 10 kips. So my question is, what is MU at the middle span? Right, I draw my moment diagram. I want to find out my MU at the middle span. So what is my MU? How do we get this MU? First, what is MU? I don't know, Bob. My farm, we have cows. They do, that's MU, isn't it? Yeah, sure, that is MU. But what does U represent? Ultimate, right? U represent ultimate. What does ultimate mean? Ultimate means 1.2 what? 1.2 what? That, right? Plus what? There you go. So that's how we do it, right? 1.2, 1.6. Now, what is MD? Dead load moment. 3-point load configuration, mid-span moment, P, D, L over 4. Isn't it? Remember that? So what is it? Come on, 8 kips, L 20 feet, divided by 4, what I get? 40 kips foot. Okay. What is my live load moment? PL over L over 4. What is PL? 10 kips, length 20 foot, divided by 4. So what I get? What I get? 50 kip foot. Nice. And my total moment, MU, equal to 1.2 dead, that is 1.240 kip foot, plus 1.650 kip foot, So what do I have, folks? Come on, help me out here. On the contrary, I suck at mathematics. All right, I admit it freely. So you will help me out. Okay, don't stare at me or I call Siri up, right? Punch in numbers, let me know what you have. Come on, folks. So louder. 128, great. That is number I have. Okay, so that is how you calculate the ultimate load. Okay, all right. So this is applied load. This is number you use for design. Okay, this is number used for design. So quickly here, how do I design buildings? Need to have equations, right? So let me give you a hint. Start with phi mn, phi mn, right? Not chi epsilon, not pi, whatever Greek alphabetic you've seen before. It's phi, okay? Phi. What is phi? What is phi? Strength, reduction factor. Oh boy, I'm in trouble. Strength reduction factor. Okay. For a tension controlled member, what is the value for phi? 0.9. Okay, remember this. That's okay. Okay. For shear, 0.75. What we're dealing here, moment, right? And tension control, right? Assuming tension control, so phi equal to 0.9. But anyway, so phi mn, what is mm? Nominal design strength. Okay, design strength. Okay, and this fellow here has to be what? Greater than or equal to m. Okay, so let's assume phi equal to 0.9. Okay, and what will be the design moment for the beam? 128 kip foot. Do what? Divided by 0.9, isn't it? Divided by 0.9, isn't it? What is my number here, folks? 128 divided by 0.9. What is it? Louder, please. 142.3. Do I get a second? Nobody agree with him? Oh boy, you're like me now. Do I get a second? Okay, great. So that is correct. Okay. Now, what does it mean? It means that to have a beam that can sustain 128 kip foot of bending moment, I need to design it for 142.3 kip foot of capacity. Got it? Okay. Now, if some cheeky fellow like Babu come around and say, so what is your safety factor? I don't know. Safety factor. New concept, right? That is what? Mu divided by Mn or Mn over Mu. Mn over Mu, sorry, flipped. Mn over Mu. That is 1 over, should I say 1 over phi, isn't it? 1 over phi, isn't it? Right? So phi is 0.9. So what is my safety factor? 1.1. There you go. Got it? Okay. What is steel? Sorry, what is the safety factor for steel? You guys learn that? Steel structure? 1.5, 1.67. What is the safety factor for RC concrete, for bending, for flexure? 1.1. So who's safer? They are safer, isn't it? They are safer. Okay. So just some fun facts. Okay. All right. With this, you shall be able to do homeworks now. Okay. You shall be able to do homeworks now. Any questions? Let me know. Okay. Any question? Let me know. Take your whole look. Take a look at your homework. Scratch your head. Hate me for a second and call me back. Okay. Find time for you. Okay. All right. Time is up. Let's hit for a 5 minutes break. We shall return around, say, I'll give you guys a little bit more time. Say 2. That's too long. Maybe 1:55. 1:55. Good. Okay. 1:55. Okay. I see you in 1:55 here. Okay. Scratch your legs. Stretch your arms. Got some grievance? Come talk to me. Or simply just want to know me more. Fine.
doing concrete testing this morning actually
Sure.
for Southeast wastewater treatment plant. And so we tested the air content first, and
What you got for air content?
there's a 3.5.
Oh, that's not too bad. Yeah.
It's for exterior.
Right.
So they added air entrapment.
Yeah.
We'll be going over like the admixtures.
Yeah, I see. Okay. Yeah, I was going to say on the low side of it, seems like, but that's okay.
Yeah. So after we tested after air, it was like 5.8. So it jumped almost that much.
Right.
It was interesting.
Yeah.
But yeah, it's kind of cool to see how they relate from this class.
Yeah.
And like doing that.
I'm actually I'm a ACI certified level 2.
Oh really?
Yeah.
I haven't gotten a certification yet.
Yeah.
They haven't done that for me because they didn't want to invest the time because I'm an intern.
Right.
But yeah.
Try to get it. They bump on your pay.
Yeah, I know. I do want to get it. I do want to get it.
Yeah, it's just a tiny car,
Yeah.
but you have to go through some training. And
Yeah.
you do that for asphalt tests as well.
Yeah.
Asphalt probably gets you more.
Yeah.
Yeah.
I didn't know if there's some kind of certification through school I could do that. before.
Talk to Dimitri Faze,
Phase.
Dr. Faze. He's in charge of ACI chapter here. I think they might get you a discount or something like that.
Okay.
For me, I think it was $95, but they sent me for a course, and okay, they usually don't have undergrad students doing the certification. Most of them are like old technicians, no college educations. I went there. They went there for the free barbecues mostly. Yeah, but you need it. You can also build your way up. I was the construction material testing lab manager for about a year. We went through, our lab went through the AASHTO accreditation program. Someone from DC actually coming down here, inspect us, everything. So I was maintaining our hydraulic machine, oil spilling, the fluid spilling, had to find the pressurized pipe, the whole 9 yards. Sweep the concrete, debris and everything, clean up the machines, the sulfur cap, maintain it, clean up and everything. So
Fun time.
You want to probably try to get the design aspects of it. I don't know if SCI also do it. I don't
They
know.
really don't do much design.
Right, consulting, right? They probably do some consulting. Yeah, they want to get on the consulting side of it, and you probably won't be the guy stamping it, but if you work with a PE, whoever stamp on it, you can read their consulting opinion just to get some experience with it.
Yeah.
It's actually good money.
We have a geotechnical department too. They do some more of the geotech reports, and they do more some of the design, geo side. But there's a lot of certifications, a lot of different options you can do with materials testing. For some,
it's always good to get a certification early. A later stage, you just carry it with you and everything. It carries certain weight. When I was there, we always go to a job site and do inspections for them. So when you show when you show certification, the civil engineer respects you, or else they just see you like a regular technician. They don't want to talk to you. You know what I mean? You're like just a guy do the wheelbarrow and everything.
I feel that.
I had a lot of good experiences. We used to also run I don't know whether they do that now anymore. They do the soil testing. There's a kind of like a nuclear.
We do that.
You do that too, right? And we had to actually maintain them, lock them.
Double lock them inside, double lock it to the truck.
I got a guy, shouldn't say his name, but anyway, he's Michigan grad and he's pretty smart and everything. He actually lost the key on site. I gotta drove 4 hours just get there and bust it open, get the equipment out, relock and everything. Oh boy.
It happened to one of us. He had the key, but the lock was open. At the job site.
That's horrible.
So he called me. He's like, "What do I do?" I was like, "Just break it off somehow." Like this so
it's horrible.
Because the truck contractors are so bad.
They have very strict regulations about this stuff. I remember I had to call the Conway truck just to ship like 1 millimeter because it's supposed to have their materials and everything, right? So it's interesting life experience. So good. You're learning a lot of things, I guess.
I think so.
You think about getting EIT and PE this route? Afterwards? You might want to consider doing EIT early because I think whatever intern experience counts towards PE. You can still put that in.
Oh, really?
All you need to do is probably talk to your supervisor of the company, ask him or her to give you a letter. And then end of the intern, you say that this counts towards my PE. So
I didn't know.
you should do that. Shorten time, right? PE is the thing, right? What's up?
The consequences of floating rebar as you pour it.
Okay, that's bad.
I've
seen that before.
And like I jumped down into in the pit, and I took the rebar with me, and I was bending the corners. I was about to create a frame and extend it up, create another frame, and then
Yeah, I had experience like that before.
yeah, they're quick and cheap, and they're just throwing up cookie cutter houses. And I was like, what are we doing? And like the guy who'd been there, he's like, what are you doing? Get out of there. I was like, okay.
So there are two type of group there, crew there. There were edited and there are unedited. From a practical point of view, if it's not gonna hurt your cage, like it doesn't jam you, you should just leave it alone because it's too dangerous as you get into the country and everything. But then again, if you have a critical location, the stress can and sometimes you just disrupt the cage.
There was nothing. They literally just like dug out, and
then they probably
yeah, they I was like, okay, you might be supplying roofers out in 10 years when these houses are messing up.
you will be amazed how
Maybe 2 years later.
yeah, I think you'll be amazed how uniform construction policy.
Yeah.
So yeah, I hope you manage
Exactly. Yeah.
Yeah, good to know. Good to know. Yeah, all right. All right, guys. It's 1:55. Come on, let's get started. You want to go home? Me too. When you want to go home to rest, I have more work to do. So let's get on to it. Okay. Now, today, we just talked about the basic concept, right? And I want to go a little bit fancier. Okay. So I'm going to start drawing some nice drawings and show you what the behavior of these properties really are, and also some equations along the way. Okay. So design properties of concrete and steel. Okay. Design properties of concrete and steel. Okay. Now, keep in mind, these are not real behavior, but more like a simplified behavior for design. Okay. Now, you can find this from your textbook, chapter 4, chapter 5. Okay. And objective is that we need to understand objective 1. That is understand the concept of flexure design. Okay. Concept of flexure design. Okay. For this part, I think for today, we will get mainly into the cracking moment. Okay. We'll get into the cracking moment today. All right. Maybe a little bit compressive zone. We'll see how that goes with the time. Okay. Compressive zone. Okay. All right. So first, steel. Now we said steel looks like a nice simplified two-stage behavior. And if I call this Fs and I call this epsilon S, and it should go like a linear curve beginning and then flatten out. And you have a yield strength called Fy. And the other way, this is in saying compression. And let's say compression is positive and then goes the other way is negative in tension. Now, let me ask you this. If the yield strength for steel is Fy equal to 60 KSI, what is the compressive strength of that steel? Steel, right? Not concrete, steel. If the yield strength of grade 60 steel 60 KSI, what is compressive strength of that steel? 60 KSI, right? What is the tensile strength of that steel? 60 KSI. Okay, so steel is so-called symmetric materials. Okay, symmetric in terms of compression and tension, meaning it behaves the same if it's in tension or if it's in compression. Okay, or if it's in compression. Now, the plateau or the yielding turning point here, I see a red color. You guys see red or black? It's just my eyes. Okay. Okay, good. All right, I don't know. Anyway, so the strain at yielding is called epsilon Y. And epsilon Y for compression and tension should be same. And that number is a constant. Regardless of what type of grade of steel you have, that number for yielding is constant. And this number, you need to remember that is 0.00 what? 0.00207. And this is for a grade 60. Okay, grade 60. Now, how do I get that number? How do I get that number? I get that number because this is Young's modulus, the slope of this linear response. So Young's modulus for steel is what? 29,000 KSI, right? So for grade 60, I have yield strength epsilon y equal to Fy divided by ES. Fy is 60 KSI and ES is 29,000 KSI. Unit cancel, KSI, left you with 0.00207. And that is the yield strength of the steel for grade 60, okay? For grade 60. So box it up, start it. So you will need to remember this. You will need to remember this, okay? Same thing here, need to remember this. All right. So yield strength is constant for same grade, right? For same grade. Get it, grade 60, always 0.0207. And we actually use this number in design a lot. Okay, so need to remember that. Okay, so that is it for steel. So three things: Young's modulus for steel, 29,000 KSI, yield strength 0.0207 for grade 60, always grade 60, and symmetric materials, meaning behave the same in tension and compression. Now, why is that? I feel, my personal feeling is steel is not good for compression. Remember, concrete is good for compression, right? Why is that? Because when you think about Eiffel Tower, right, steel structures, right, what do you feel? Is it heavy or light? You feel light. You feel it's light. Why? Because it's empty, right? It's lattice structures, a lot of holes opening in it, right? So steel structure are actually very heavy, so we make them like lattice truss, meaning spatial, right? Rod members, right? It's like slenderness, like my pen, isn't it? That's how we usually make steel. Okay. So what happens if I start compress the pen? It will do what? It will deform and then get outside this plane called buckle. Okay, and that buckling load is much lower than the yield strength of the steel. Okay, so most likely your steel will fail in terms of buckling, not in terms of yielding. Okay, it is only in tension, your steel fails in yielding. Okay, so that is the reason why you feel that the steel is not good for compression. Good example. Have you seen the post-earthquake structures in Japan? Of course not, right? Google it, right? You see that the column, the bend cap of the bridges are gone, crushed. You see a lot of steel coming in all kind of weird shapes. What will happen? What will happen there is that in the compression, when the concrete goes, so goes steel. Okay, there's no support to the steel anymore, right? It's like my lips and my tooth. When I lose my lips, my teeth exposed and it's cold, right? No support. Lose the concrete, the steel become sticks, right? No support, so they buckle, they fail. So steel cannot take compression in reinforced concrete structures because of this reason. Got it? That's why we say concrete is good for compression, steel is good for tension only. Understand? Okay, all right. So that is that for steel. Now, concrete, right? So symmetry, let me just finish this so I have a good picture here, okay? So that's for steel, okay? Now concrete. All right, so concrete. We have talked about F prime C and everything, but literally the stress strain curve for concrete looks actually like this. In compression again, and assume it's positive, right? Compression again, the curve shows a linear behavior at first, then goes into the hardening stage and then softening stage. All right. And then at the peak, it has a strength called F prime C. That is the compressive strength. Okay. And then corresponding to that strength, we have a peak strain, epsilon 0. But listen to me, nobody care about epsilon 0 for concrete. Nobody care about it. We labeled it, but nobody care about the value of it. Everybody care about this value though, is that the failure, we call it epsilon Cu, compressive failure for concrete, okay? Everybody care about this value because that's the maximum strain a concrete can sustain, okay? And ladies and gentlemen, that value, epsilon Cu is, and you need to remember this, 0.003, 0.003, okay? So that number, you need to remember it, okay? Need to remember it.
What's the subscript on that?
Epsilon Cu, like a copper. Yeah, CU. Compressive at ultimate CU. Okay, option C. Remember this. Okay, remember this. All right, so that is about it. And now Young's modulus of concrete EC equal to 57,000. Need to remember the equation, square root F prime C, square root F prime C. And again, F prime C in terms of unit is PSI. PSI. Okay. Now, one funny concept. If I stack against or step up the steel against concrete, which means I use ES, Young's modulus of steel. Again, what is that number? 29,000 KSI. I will drill you to death, but you will remember this number, okay? Over EC, that is 57,000 square root F prime C, okay? And let's say this F prime C is 5,000 PSI. Then what do I have? 29,000 KSI divided by what? Come on, calculators, guys, calculators, help me out here. What is EC for a 5,000 PSI concrete? What is it? Come again? 57,000 square root of 5,000 in terms of PSI. What is it? 1 million. 4 million. Okay, so 4. Let's get an exact number here. For what? $4,700,000. 4,009. Is that what you get? Let's go easy on me. 4,3 what?
403.
403. See, told you, right? Still not good at English. 403 what? 0509. Thank you so much. I apologize. Okay, my mistake. All right. This number is what? In terms of what? PSI or KSI? PSI. Let's do KSI, right? So what I have? Right? So cancel that, what you get? 29,000 divided by 4030.509. What you get? 7.2. So shall I say if I use 4,000, it's probably going to be something like an 8, right? So what I have here is that this is a new definition, okay? We call it modulus ratio between the steel and the concrete is roughly between 7 and 2. Sorry, 7 and 8. Now, what does that mean? It literally means that 1 inch of steel in terms of stiffness, rigidity, okay, hardness, 1 inch of steel equal to 7 or 8 inch of a concrete. Okay, so who is the more badass here, steel or concrete? Steel is. Steel is actually. So why we're not using steel as compression? Because it buckles, and it's actually expensive and heavy, right? So that's the sole reason we're using concrete here. Okay, so we will use this later in the game, but right now just need to remember this. Okay, all right. So this is about compression of the concrete. Okay, compression of the concrete. Now in tension, we get on going, get on going, get on going. Should I see the same thing in compression? Should I assume concrete is symmetric? No, right? Why is that? Because it will fracture, right? It will crack, right? And what strength it will crack? F modulus of rupture is what? FR, isn't it? FR, where you at it? 7.5 lambda what? Square root of what? F prime C. Okay. Where you at it for 5,000 PSI for normal weight concrete, that is what? 530 PSI. Okay. 530 PSI for F prime C, 5,000 PSI. Okay. You remember this number? Exam, you're gonna go very fast. Okay. You don't remember, you have to punch your calculator like your keyboard when you play Call of Duty, right? So don't do that. Okay. You don't want that. All right. So it's linear till you hit peak strength and you break, right? And then you see quickly a softening stage, just like that. So this means what? Concrete is so-called non-symmetric or unsymmetric materials. Okay, it is not symmetric, meaning the compressive behavior of concrete is different from the tensile behavior of concrete. Got it? The compressive behavior of the concrete is different from tensile behavior of the concrete. Now, the compressive behavior of steel is the same as the tensile behavior of the steel. Okay, so they're different. Got it? All right, very important. We will have that in the exam. We'll have that in the exam. Okay, unsymmetric. All right, so you see, these are the number games. Okay, so what do we need to remember? We need to remember this guy. Okay, and we remember this guy, right? The epsilon CU, right? And we remember, of course, this modulus ratio, but you won't need it right now. But most important thing, we need to remember this fellow here, okay? Tensile strength, tensile strength. All right, so that's as far as we need to worry about the properties of steel and concrete. If I were you, I would take a snapshot of this and print it as a creep sheet on your big A4 paper, front and back, letter size for the first exam, okay? I'll do that just for the sake of it, simple, okay? All right, so that's it. Now, we need to talk about the bending. Okay, talk about the bending. So now we know how concrete behaves, right? And I start building concrete structures, right? Imagine I'm a caveman, right? Caveman. I just like play mud, right? I just put the concrete together. No reinforcement in my head. Pure concrete. I love concrete, right? I have a beam like this. Let me change the color and say that this is to study cracking moment, okay? Study cracking moment. I build a beam like this, nice long beam, okay? And I say, look, I am bending it, okay? And never you mind, is it a 4-point bend, 3-point bend, but something like this, maybe let's say 3-point bend, I exert some bending moment to my beam, bending moment to my beam, and I have a length of it, and let's call it L. And the total force, you know, is P, and I want to bend it, right? So first thing first, where my crack will start from, bottom or top? Bottom or top? Bottom, right? So that's where my crack's gonna start, okay? When my crack will start? When? Well, Baba, I don't know. You tell me. Well, I don't know neither, right? So, but let's think about it. Why concrete will crack? Why the concrete is cracked? So the tensile strength of the concrete here has been breached, basically, right? So the stress in the concrete Fs reaches to the tensile strength of the concrete F modulus rupture Fr equal to what? 7.5 lambda square root of prime C. So it is at this moment, concrete cracks, right? Once concrete crack, what happened? Your section becomes smaller because cracked section doesn't have any strength at all, right? So the crack propagate all the way through your beam and you become two pieces, right? Like the Shaolin monk, right? One palm cut into two parts, right? So to calculate the moment, we use the old friend moment calculation equation MCR, I call it cracking moment. That should equal to what? FR, which is the tensile strength, multiplied by IG, oh boy, moment of inertia, okay? Moment inertia, divided by the distance between the neutral axis and the mostly stretched tensile fiber, in this case, half of my height, which is YT, okay? Shocking, of course, because we forgot mechanics materials, right? So let's review a little bit. How do I get this equation anyway? Remember, in mechanics materials, we're looking at this section right here, remember? Okay, we say that let's take the shaded section out. This section, let's just say it has a width of B, height of H. What is its moment of inertia, IG, for this section here? 112 what? B H cube. You took from Nick or me?
I took it from there.
Oh man, one for Nick and Neil for Bob. 112 BH cube, okay? 112 BH cube. That is for the moment of inertia. Now, the tensile stress right here is FR, okay? Neutral axis for rectangular section is right in the middle. So the distance between the neutral axis to the tensile fiber is what? YT equal to what? Symmetric, so YT equal to what? H divided by what? 2. Okay, so I want to find the stress, right? So FR from the review should equal to moment exerted MCR multiplied distance YT divided by IG, which is moment inertia. So that's how I get this equation, right? Just flip around. See it now? You guys see it now? Remember this? Mechanics materials? Okay, so that's how I get it. That's how I get it. Now, since for most of the beam we're dealing with here are usually rectangular, BH, okay? Let me simplify even more. So now I got this equation, right? I say MCR equal to FR. What is FR anyway? What is FR anyway in English? Not in Chinese. What is FR? Modulus of rupture, right? What is in Chinese? I mean, mathematically, 7.5. Did I wake you up? Yeah, I should. 7.5 square root of prime c. There you go. Sorry, no offense, okay? I'm just making jokes for you guys to wake up, okay? 7.5 square root of prime c, right? That is FR. Now, what is my IG? What is IG? 1 over 12, what? BH cube, and that is on the top. What is on the bottom? YT. What is YT here? What is it? H divided by 2. So this, I can simplify that. So MCR essentially equal to 7.5 square root of F prime C, and this become what? BH squared over 6. Got it? See it, guys? Okay. So you have choices now. Either you remember this equation, which is fine, cool bean, right? My wife always say that, I don't understand, but anyway, cool bean, right? Or you can use Bob's equation, right? My favorite, Lindsay equation, right? Okay, but I can plug in directly, knowing that it is rectangular section. Okay, BH has to be a rectangular section. Okay, it's up to you, whichever equation you want to use, all right? So we get the cracking moment. Okay, you say, Bob, all right. We got a cracking moment. Don't look at me. I'm not McDonaghy. I'm just trying to play his part. So what do you use for? I don't know. We have the cracking moment. That's it. So what do you use for? When concrete beam will crack? When you're on the job site. When you use the crane to lift it up to assemble it, especially for precast, isn't it? So on the crane, what do you see? Oh, I don't know, Bob. I'll give you a scenario, right? So I have a beam. How do you lift it? The concrete beam is crane. Well, those precast babies, right? Those precast babies, right? They have hooks, right? Like that. You hook them on and you lift it, right? Say, when you do that, what's happening? You have self-weight of the beam, isn't it? It's heavy, isn't it? Right? And you have 2-point lifting it up, right? 2-point lifting it up, right? So in my head, looks like I have a side view like this and applying a 2-point load like this and applying distribute like that, right? That's what's happening for the beam, isn't it? That's what's happening in the beam, right? Now, geniusly, I thought, hey, look, it doesn't matter which direction or which side I'm putting these loads, right? So let me just put these loads on the top. Put these loads on the top and put these loads on the bottom. Can I do that? Why not? Sure you can. And of course, sorry, the lovely division line gone here. I can do that, can I? I just flip the side, the same thing, same load, right? Now, what does that look like? That look a lot like a simply supported beam under distributed load, isn't it? Ooh, mechanics materials, right? Mechanics materials. I'm not doing a free advertisement. If I'm doing that, please join my mechanics materials class next semester. But anyway, so that looks like this. Right? Say the distance between the hook is L. That is my span length actually. And the dead load of my beam is say omega. Okay. for a distributed load, okay, simply support it. What would be the max moment in the middle? Nick's favorite? Just kidding. What is it? 1/8 omega L squared, isn't it? Neil for Nick, 1 for Bob. Come on, remember this, okay? I'm just joking. Go back to see your mechanics material, at least the structure analysis part of it, okay? To get ahead for this class, okay? Don't remember, just basics, okay? So that is the moment, isn't it? So now, that is the maximum bending moment of me cranking up a beam, right? Cranking up a beam. I don't get to say how much of a lifting power I have. That's my company, right? If it's cheap, low capacity, rich, big capacity, I don't know, right? I don't get to say how long my beam had to be, isn't it? That's the contractor, whoever made the beam, precast, everything's too late. I'm just a lowly guy trying to lift it up, right? But if I want to make by bucks, there's only one thing I can do is to control the distance between my hooks. That is control the span length, right? How do I control it? So this is how I control, right? I have this equation right here, right? So I say the length square has to be what? Has to be smaller than this smaller. So let me set this way, you see that clear. So this will be the cracking moment as control, isn't it? Cannot exceed my cracking moment, right? So this has to be bigger than this. Is that right? Bigger than this, right? So L squared has to be smaller than A times MCR over omega, meaning my span length critical, I call it cracking span length, has to be smaller than square root of A times MCR over omega. The omega is my self-weight. And to tell you the number, omega is 150 pounds per cubic feet for concrete. Okay. So if I'm smart enough, I will make a table for myself hanging in my crane operator room, right? To tell me that if my beam is this long or my hook distance this long, I can handle it or I can't. Can you see it? Right? So who said concrete is not fun? It's a lot of fun, right? You can actually use it. You can actually use it and make money, right? If you're good enough. Got it? All right, so what I'm trying to say here, cracking moment is the first threshold. You don't want to hurt. You have a beam, you have a structure, you don't want to crack, right? Okay, so that is how we calculate cracking moment, MCR. Okay, remind you again, two equations, right? This guy here or this guy here, whichever one you want to use, okay? For the simplicity of it, I'm just gonna write FRIG over YT, which is half H for this case, okay? So that is the cracking moment. All right, okay, let's do some calculations, right? Might as well. I am having a beam on site. I say that the cross section. So let me raise this up and say example. Okay, I'm having a beam like this on site, and my section has a width of B equal to 12 inch. And again, this is Bob's favorite, okay? You see 1 foot, 2 feet high beams all the time. I know it's weird, it's small, but that's how Bob likes it because it's simple for calculation. Okay, so 1 foot wide and 2 feet tall beam, okay? I want you to find out the cracking moment for this beam if my concrete compressive strength is 4,000 PSI, curbside concrete. Okay, all right, so that is example. So where do we start? I don't know, Bob, you put the hooks in? Wake up, we're not there anymore, okay? Just trying to calculate the cracking moment, MCR. So where do we start? We start from this equation, right? FRIG divided by half H. Remember this equation? So first thing I need to find a modulus of rupture FR equal to what? Equal to what? FR equal to what? 7.5 lambda, which is 1.0 for normal weight concrete, square root of what? F prime C. What is F prime C here? 4,000, right? So punch some number out, please. Help me out. I suck at this calculations. My algebra is like what, D in college, and I'm not kidding you. Okay, help me out here. 7.5 square root of 4,000 PSI. What'd you get? FR.
474.
474 PSI. Now, for exam, right? Why are you in exam? How do you know you got the right number? I want to make sure I'm right, step away, right? I don't want to make, how do I know? It's about 10%, right? What is my compressive strength? 4,000. So it's about 400, right? So I'm okay. Around that level. So I'm fine, right? So I know I'm right. Got it? Quick check. Double check always, right? Make your things go easier. Okay. So now that is set. So MCR equal to FR IG, you know, in this sense, IG is 1/12 BH cube and divided by YT, half distance, so it's H divided by 2, right? So FR 474 PSI for 1/12 and B 12-inch, which is height 24-inch to the power 3 divided by H/2. H is 12-inch, 24-inch divided by 2, so it's 12-inch here. So that is in the bottom. So what do I have here, folks? Come on. What is it? 474 divided by 12, multiply 12, cancel it out. And there's a 12 here. There's got to be 12 to the 3, multiply 8. And there's a 12 again. So this is 12 square. Let's do a competition, right? I'm doing by hand. You're doing the calculator. See what you get, right? 474 PSI multiply 144 multiply 8. So what do you get, guys? 546,000 and 440. Do you get this or different? 42. Okay, close. Good. That's correct. Okay. And what's the unit? Where are you at, Miss? Think about it. Think about it. I have PSI here. And this, what is the unit for moment of inertia? Inch to the what? To the what? For a moment inertia, inch to the what? Power of 4, right? Why is that? B H cube, right? So inch to the power of 4, right? For a moment inertia, inch to the power of 4. That's okay, right? So what is the unit for height? Inch. So what do I get? Inch to the what? 3, right? So after all this, I get inch to the 3, right? So PSI multiply inch. PSI multiply inch to the 3, right? What is PSI? Pound per what? Square foot, right? So 3 inches, right? Square inches, right? Right. And multiply inch to 3. What do I get? Pound inch. There you go. So MCR is 546,441 pound inch. Okay. And now convert that to kips, 1,000 pounds. Okay. Convert that to 1,000 pounds. What do I get? 546.441 kips inch. Is that awkward? Yes, it's awkward. Why? I don't like kips together with inch. I like kips with foot. Okay, so convert to foot, MCR to what? 546.441 divided by 12, kip foot. Folks, what do we have? Let's do a division. 546.441 divided by 12, what do I have? 45.54 kip foot. Okay, that is my final number on the cracking moment. That's it. So if your moment exceeds that level, you're going to see crack in your beam and an irreversible crack. Your beam is going to be gone. All right. So that's how we determine the cracking moment. Quick thing here. From this moment on, ladies and gentlemen, we will only take, I say this once for all, we will only use kip foot as a unit for bending moment for design. Only kip foot. If you show me pound inch, have a million number, like 4 million, 5 million, I am gonna go bananas and will give you 0 point on unexamined homeworks, okay? I swear I would do that, okay? Why? Because on job site, you will not use pound inch for a moment. It's too crazy, right? Too big a number. So always round it up to kip foot, okay? Please, please help me to help you, okay? Please, kip foot, kip foot. All right, so that is about cracking moment. Okay, I still got like 7 minutes. So I'm gonna start talking about compressor zone a little bit. Okay, but before that, any questions? Are we okay? Are we okay? Not too bad, 7 minutes, all right? Just sip of water, pretending you don't see me in my head. You're fine, right? Okay, 7 minutes. All right, 7 minutes. So now we know a concrete beam sitting there alone or when lifting up, they will crack, isn't it? It's bad. So we have to put reinforcement in it. Okay, so we put reinforcement in it. What's so big deal about it, right? So we have a beam laying down here and let's put some steel in it. Okay, put some steel in a blue indicating steel, and one steel bar like this, one steel bar like that. Okay. Okay. So once I put steel in it, I start to bend it. Apply bending moment. All right. And remember mechanics materials? No, I don't. That's okay. I'll draw you a picture, right? So one theory you should remember from mechanics materials that plane section remains plane in bending. Let me say this again slowly, okay? Even slower. Plane section remains plane in bending. What does it mean? It means that think of your beam like a loaf of bread. Think of your beam like a loaf of bread. What does loaf of bread look like? Slices like this, slice like this, slice like this, slice like this, slice like this. Okay. Now, when I bend it, okay, from side view, it looks like this: 1, 1, 1, 1, 1, 1. These slices together, right? Chain together. Okay. When you bend it, what's really happening? What's really happening? Well, what's really happening is that if this is the center, this section stays the same, right? The section here rotated, isn't it? That's what loaf of bread would behave if you bend it like that, right? It will rotate, isn't it? But it's still straight. See, still straight, right? So this loaf of bread will bend like this, right? This slice will bend a little bit more. The slice bend a little more, slice bend a little bit more, right? So you connect the line that give you the bended beam. You see that? Do you see that? That is called plane section remains plane. Okay. So curvature is caused by linear rotation of the planes of these constructs. Okay. All right. Knowing that what's really happening at the bending is that say I have a maximum moment in the middle section, right? Say that I have a lot of bending going on. So meaning I will have a compressive strain on the top, and when it fails, it's going to reach the maximum strain in the concrete. And what is the maximum strain in the concrete? Well, I don't know. Bob, you drew me the curve before. So let me go back to see. When concrete under compression, it fails at what? Epsilon Cu, isn't it? And for epsilon Cu, the number is 0.003. So meaning if I bend my beam and happen to be my top fiber, crush it to a 0.003, my beam will fail, right? Because concrete crumbles, and that's it, right? So that's that. Now, for the bottom steel, when it fails, right, when it yields, right, it will reach what? The critical strain, right, at yielding, which is what? 0.00207 for grade 60. Okay, so we call this a perfect moment. A perfect moment. Okay, and you notice that this is nice linear line. Why this is a nice linear line? Because plane section remains plane. It basically just rotates, right? Strain level, it just rotates. Okay, and trust me, I will not bother you with heavy mathematics, but one thing you should think of it. Although strain is linearly distributed, stress is not. Why? Because the stress-strain relationships for concrete is not linear. It's curved, isn't it? It's curved, isn't it? You don't have to calculate it, but in your head, you should know that although the strain distribution is nice and linear, the stress distribution is not. Actually, this is what the stress distribution looks like. In the top, you see a lot of compressive stress like this for concrete. And since concrete has no tensile strengths at all, we assume whatever intention for concrete are gone. Meaning at the lower half of neutral axis, no concrete anymore because they're cracked. The only thing left is what? Still reinforcement left and give you that yield strength of Fy. So this, ladies and gentlemen, is the stress distribution, and this is the strain distribution in the diagram. Okay, all right. Now we'll talk about this again next lecture, but you will see this. If you draw this in exam, no question asked, I will give you 20%. No question asked. If I see this strain stress distribution diagram, No question asked. I'll give you 20%. How nice am I, right? Trust me, you will forget this. Okay, you will forget this. So I'm telling you again, if you just blindly draw this, right, this will help you. Okay, you draw this, give you 20%. No question asked. Okay, you don't draw this, you lose 20%. Freebie, okay, take them, take them. Okay, now I want to lead into the next lecture just a little bit. Okay, so forget about the heavy mathematics for now. Think of this way. Do you want to find out exactly this hyperbolic line is in terms of mathematical equations? Do you want to do that? Raise your hand. I don't see a fellow nerd. Just me, myself, right? Yeah, that's about right. Tell you the truth, I don't want to do that either myself, right? It's crazy, right? For a guy, structural engineer on the job site, give me 2 hours, I got to come out with a number. I am not going to do that. Even give me 10 computers, I'm not going to do that. So what we do, we simplify as civil engineers, we approximate, we do quick shortcut solutions. So what do? We say, actually, Sir Whitney, great guy, Sir Whitney say, forget about this parabolic BS, right? I want something clean and simple. Okay, so how simple? Let's do square. Just like that. Guy's a genius, right? Guy's a genius, right? He said, you know what? Forget about it. I'm going to square. And so perfect that I say, I am going to keep the width or the strength of the square to be perfectly 0.85 F prime C. Don't ask me how I did that. Actually, he went through the mathematics, okay? He did that, hyperbolic and everything, okay? But he simplified. So you can keep it approximated as a 0.85 F prime C, the width block, okay? And then let's say this height is called A. And this A is a little bit shorter than the actual compressor zone C here. And the ratio between A and C is that A equal to beta 1 C. Beta 1 is the coefficient, and that is dependent on the compressive strength of a concrete F prime C. We'll talk about that, okay? So going from a crazy parabolic line into a simple rectangular, and we call this our savior. We need stress block. Okay? We need stress block. You say, Bob, you just turn into a complex line into a rectangular. What's so great about it? I can do that. What's so great about it is this. If I get this compressor zone into a block, then the total compression force from this block equal to the area of this block, and that equal to 0.85 at prime C, what? A. Is that right? And remember, this is a beam, which means has a third dimension, right? Has a width of B. So this essentially is AB. And that, ladies and gentlemen, is the total compression of the concrete. No parabolic, no finding the centroid, nothing, because it's rectangular, right? The centroid is the middle of it. So simple, so beautiful, right? And guess what? It's even more beautiful because in the bending beam, you have compression. Naturally, you have to have a tension to equal that, right? To balance that, right? Tension have to equal the compression when you do a cut. Remember, in next class, when you do a cross-section cut, total compression has to be balanced the tension, remember, right? So what is the intention? Steel, right? And what is the strength of steel at failure? F what? F what? Y, because it yielded, okay? And if I know the area of steel, that's how much I put in, that is AS. And guess what? You just reach the balance between compression and tension. Isn't it? Isn't it? Last question. Do you know how much steel you put in a beam? You better. I mean, that's you actually designed it, right? You better know that. So you know AS. Do you know the yield strength of the reinforcement steel you put in? You better, because you told the guys it's 60 or 40, right? Grade 60 or grade 40, right? Whatever you put in, you need to know, right? So you know actually this part. You know actually this part, right? Do you know the concrete compressive strength? Sure. We test them, right? We know them. We actually Colorado already makes them, order them, right? So we also know F prime C. Now, do you know the width, the section size of the beam? Of course, I drew it yesterday. I know it, right? So you also know B, right? The only thing need to be determined, Genius, Whitney says, is just the effective compressor zone A, isn't it? And so happen to be A just equal to Fy As divided by 0.85 F prime CB. Now, what does it mean? Means that when you design a beam, you can estimate the effective compressor zone of concrete. Okay, you say, why do I need to know that? Because if you know the compressor zone, you know the centroid of compression force. You know the location of the bars, you know the distance between the centroid of compression to the centroid of tension, right? Then the moment resistance equal to compression multiplied by the distance between compression and tension, you know the design capacity. Okay, so just like that, you should theoretically know how to do moment design for a beam. Okay, we will get to the nitty-gritty details next lecture. Okay, so homework, I'll send it, but most likely going to be on cracking, simple things. Okay, so thank you for sticking with me today, and we'll see you on Monday. All right, see you on Monday. Okay, thank you. Guys online, we're ending the lecture now. Okay, so I recorded it on my desktop and I'll upload it to the YouTube. All right, thank you.